How's it going, everyone? Okay, today we're going to look at section 9.9, and I think this will be the last section we look at in this chapter, and then, like I said, Thursday we'll review, and then we'll be able to, so review Thursday, and then starting from Thursday until basically the Monday after Thanksgiving, so a pretty big window that we could we'll have to take this exam. Take this exam, and that includes 2 weekends. So should be plenty of opportunity for you to find a good time to do it. Probably you will want to take it before Thanksgiving. I would just add, hopefully you're staying on top, staying up to date with everything. You'll still be fresh, and they'll be better. And then, Anyway, so 9.9 is on the representation of functions by power series. Okay. And the basic concept is from geometric series, actually. A geometric power series is a little bit more specific way of saying it. So we'll look at a geometric power series. Now, the idea, if it's a power series, like geometric series, let's look at that first. Our geometric series was the sum, n equals 0, I think it was 0 to infinity of a times r to the n, which was a times 1 plus r squared plus r cubed plus r to the 4th, etc. There's an extra r in there, damn it. R to the first, r to the second, r to the third. There we go. Sorry about that. That's just our basic geometric series right there. But we look at a geometric power series, and basically instead of having the common ratio r, we use this value x instead in its place. So our format will be n equals 0 to infinity a sub n x to the n, which will be a0 plus a1x plus a2x squared plus a3x cubed, and so on. In fact, we may not even need the an. Yeah. an equals 1, we could say n equals 0 to infinity of x to the n is 1 plus x squared plus x cubed, and so on. And in fact, we could actually figure out the sum of that. The sum of that is the first term is 1, common ratio is x, and so their sum is a over 1 minus r, so it's 1 over 1 minus x. Start with that. Okay. Now, ultimately, our conclusion is here, let's not even consider the coefficient case. I don't know why I wrote that one down. It's easier to start from here, and this establishes a pattern for us. If we have, just 1 plus x squared plus x cubed, this is just a basic power series, actually. But it's considered geometric because we have a first term and we have a common ratio because we're multiplying by x each time to get to the next term. So under the conditions of a geometric series, the sum being first term a divided by 1 minus the ratio r, which is x in this case. Our first term is 1, our ratio is x, so it's 1 over 1 minus x. So, long story short, our conclusion that we can draw now is that 1 over 1 minus x is equal to the sum of n equals 0 to infinity of x to the n. Okay. Now, related to that, we have the sum n equals 0 to infinity of negative 1 to the n times x to the n. So the question is, how does this being an alternating series alter the outcome? Well, it starts off 1 and then minus x plus x squared minus x cubed plus x to the fourth minus x fifth, so on. That's alternating signs. Starts off as plus because negative 1 to the 0, the first term is a positive 1. N equals 1 is second. Negative 1 to the first is negative 1 times x to the first, x. N equals 2 is our third value. Negative 1 squared is positive, x squared, and so on. Well, our first term is 1 in this case, again. But our common ratio, as we go from here to here, what times 1 is negative x? Well, the common ratio is negative x. So when we look at the sum being a over 1 minus r, then that would be 1 over 1, and then r is already negative, so minus r would make it positive, 1 plus x. So our conclusion is that 1 over 1 plus x is equal to the sum, n equals 0 to infinity, of negative 1 to the n times x to the n. Now, these two things, if you look at the review I posted, I actually gave them as formulas on the review. So this will be provided as formulas on the test also. So, knowing that, we can take these conclusions we've arrived at, these two facts, that we have a power series representation of 1 over 1 minus x, and we have a different power series representation, well, similar representation for 1 over 1 plus x. we can take those and use those as a basis to create power series representations of other functions similar to those. And that's what we want to work on in this section in particular. Now, in the last section, we already talked about derivatives and integrals of power series, and in this case, this is where we'll actually be able to use that. Okay. All right. Now, one thing to note, because this is certainly going to be a factor, is both of these power series are centered at 0 because it's just x to the n. It's possible that we have a series that's centered at something besides 0, and that's worth considering also. So we could say, for instance, if 1 over 1 minus x is equal to the sum n equals 0 to infinity of x to the n, we know that to be true, then find a power series for the following, which is let's say 1 over 1 minus x centered at x equals 2. Well, c equals 2 is probably a better way of saying that. Okay? Now, if the center is 2, that means instead of having x here, we would like to have x minus 2 here. Okay? So the question is, what number would go here to balance out us putting this number here? So this is a little bit tricky because we are easily confused by signs. I mean, these signs can easily confuse us. That's probably a better way to say that. So we have to be very careful as a result. So when we put this minus 2 here, because this centered at c equals 2 would be x minus 2 is our expansion. So we want to write this as x minus c, essentially. And the question is, how does that change this number? Okay. Well, this is actually subtracted a negative 2. If we distribute this minus sign, so it's minus x minus negative 2. So that's actually a plus 2 that we introduced into this denominator. Now, because we've introduced this plus 2, we need to balance that with a negative 2. So I'm going to say that should be a negative 1. And the goal is to find the number that goes here so that when these are all combined back together, it equals 1 minus x still. So you get negative 1, and then minus x minus negative 2. So it's negative 1 plus 2 makes a positive 1, and then we still have our minus x. So essentially what happens is we subtracted 2 here, but that negative 2 is also being subtracted, so technically we added 2, so we need to subtract 2 here to balance that out. It takes a little while to get used to that. Okay. It's much easier to work with a center of 0, so when we have find a center of something non-zero, we have to make sure it fits this pattern, where we have x minus 2. Excuse me. We have x minus 2 here instead of just x. And so now we have to figure out what to do with here. How do we deal with this now? Negative 1 minus x minus 2. Well, here's the larger issue. 1 over 1 minus x minus c, we can say is n equals 0 to infinity of x minus c to the n. Okay? This is centered at 0, this is centered at c. So this is just x minus 0, or plain x. And that's why that one's not too bad, it makes a direct connection. But if we want something that's centered at c, then it'll be x minus c raised to the nth power when we write it in the terms of the summation. So we want a power series for 1 over 1 minus x centered at c equals 2. That means we need x minus 2 right here in this location. There's really two things that we look for. The numerator really doesn't matter too much, because we know that whatever value we have in the numerator can just be factored out of that and just be on the outside of our summation. The numerator is not a big deal. It's the denominator we need to get to a certain form, 1 minus x minus c, or 1 plus x minus c in this case, because we can also say 1 over 1 plus x minus c is the sum from n equals 0 to infinity, negative 1 to the n times x minus c to the n. And that's an important distinction, is that we can have both of these power series basics we arrived at can be centered at something besides 0. And so we can establish that we have very similar formulas with the center of c. We just change it from x to x minus c in both places. So we come back to what we're looking at here. You know, we want 1 over, we started with 1 over 1 minus x, but we want it centered at c equals 2 when we find a power series for it. So we get the center right, but now the issue is that by making this an x minus 2, it changed this first number to a negative 1 in the process. This expression still simplifies to 1 minus x, but it now has the proper center being reflected in this expression. So the issue is we don't have either one of these situations right now, where it's 1 plus x minus c or 1 minus x minus c. It's important that this first number be a 1, positive 1 specifically. So when it's a negative 1 like this, we have to go through and change that. So the question is, how can we change this from being a negative 1 to a positive 1? Well, the easiest way is to multiply by a negative 1 over negative 1. And the reason we can do that, and again, we have to make sure whatever operation we do to the bottom, we do to the top, anytime we're working with fractions, of course. But that actually would make that a positive 1, and then we can proceed with either one of these two, whichever it ends up being. Okay. Okay. Sorry about that. All right. So we multiply by negative 1 over negative 1, so we get negative 1, and that'll change both of these negatives to a positive, so 1 plus x minus 2. Okay. Now, we want the... You can kind of see the process here. We got the center correct first. Got this to be x minus 2. We got the first term here to be a 1 next. Made that a 1. And then once we take care of those, we want to make the numerator a positive 1 also. And the only way we can proceed from here is factor out whatever number is there. There is a method here. We start from the center term, get the term before that on the denominator, and then get the numerator. And so what we end up with is negative 1 times 1 over 1 plus x plus 2. Now, we said back here, 1 over 1 plus x minus c. This is a minus 2. I'm sorry, I knew that sounded off. That's my bad. It didn't magically change, I just made a mistake. I'm just ready to start on a new sheet of paper. Yeah. Anyway, 1 over 1 plus x minus 2. There we go. Now it's correct. So, going back to what I was talking about here, if we have 1 over 1 plus x minus c, we know that's the summation, negative 1 to the n times x minus c to the n. So this will, and this has an extra negative 1 in front, but that's just carried over to the summation when we create it. And this will be negative, because we have a plus here, we know it's negative 1 to the n, and then x minus 2 to the n. Normally we would be done, but this time, because we have an extra negative 1 here, we can combine this negative 1 with these other negative 1s and make it negative 1 to the n plus 1 times x minus 2 to the n. And so our conclusion is 1 over 1 minus x centered at x equals 2, or c equals 2. I keep saying x instead of c, is equal to this power series. I feel like I could have done a better job explaining that. Let me just do a different problem now. We'll start over with a simpler problem where it's centered at 0, and then we'll look at some others that are centered at non-zero values. My textbook continues to be in the way. I'll just take out these pages and they'll be alright. I just need those two anyway. The ones with the problem. Okay. So I'm just going to toss this behind me. Alright. Much better. So, let's start over a little bit. I'm going to write down what we know so far, and we'll go from there. So these are our formulas. We know that if we have 1 over 1 minus x is equal to the sum n equals 0 to infinity of x to the n. If we have 1 over 1 minus x minus c, then this is sum n equals 0 to infinity of x minus c to the n. And in fact, if we have any function here, 1 over 1 minus some function of x, it'll be a function of x raised to the nth power. That's really the larger story here. whether it's x or x minus c or a function of x. It would be that same function raised to the nth power. So 1 over 1 minus f of x is equal to f of x raised to the nth power. Okay? So that one is also true. And then if it happens to be a plus instead of a minus there, then we know it's alternating. And that's the other thing that we know, is that 1 over 1 plus x is the sum n equals 0 to infinity of negative 1 to the n x to the n. Okay? So I just repeated this for the first one, but the same holds true for the other two. So whether we have 1 minus x or 1 plus x, the only difference is the alternating term. So the same thing would be true here. If this was plus, we'd have an alternating term, negative 1 to the n in front of that. If this was plus, we'd have negative 1 to the n in front of that. So I'm not going to write those down again. I think that's pretty straightforward. Okay. Let's start over with something centered at 0. Like I said, I think that'll be an easier place to begin. So we'll have 2 over 4 minus x centered at 0. Now, it's centered at 0, so we just have to make sure this is plane x, which that's what we have here, so that's good. We always start with this term first. Then we do this term, this constant on the bottom, then we do the constant on top. Okay. So, we know this is good because this already reflects the center being 0, so it's x minus 0 or just x. So we move to this term. We want to make this a 1. So the only way we know to make this a 1 is really just to divide everything by 4. So we make 1/4 multiply on top, 1/4 multiply on bottom, times 2 over 4 minus x. So that'll give us 1/2 on top over 1 minus x over 4. Okay. So basically by dividing everything by 4 or multiplying by 1/4, we end up with the 1 that we want right here. We have a slightly different expression here now as a result, but that's okay. This is still x minus c divided by 4. And that's what's important here. And we have an extra factor on top. We know we can factor the numerator out. Okay. Now we look at this one. It actually reflects this formula right here, 1 over 1 minus f of x. And that's why I wrote it down, is because it won't always be just x because of this, like things like this where we have a number here, we have to get rid of that number 4, so we divide everything by 4. It results in this situation that we see here. And so this is probably the best description of how we need to translate this into a power series, because if we have 1 over 1 minus f of x, we know it's the sum of f of x to the n. And we'll just use x over 4, and that'll be our f of x. Okay, so that'll be 1/2 sum n equals 0 to infinity of x over 4 to the n. Okay? And what's more, we can use the convergence from what we know about geometric series to find the radius of convergence for these power series. Just less than 1, sorry. We know from working with our geometric series test back in 9.2, I believe it was, that this ratio that's being raised to the nth power has to be between -1 and 1. So we can either think of it as the absolute value is less than 1. Now this is a less than. It kind of looks like a equal to part, but we do not want equal to here, turns out. Not all the time anyway, but this goes back to when we talked about alternating series in section 5. There's more things going on there that I just don't want us to worry about. So we'll just use less than, and that's sufficient. So we can say -1 is less than x over 4 is less than 1, and then we'll just multiply everything by 4 and we'll be good. So our radius of convergence is from -4 to 4. Okay? So we have those two as our answers now. So here's our power series, and here's where it's convergent. Okay. But I'll keep this formula page handy as we continue. Let's do some more of these, 'cause, like I said, not the easiest thing to get the hang of. So I'm going to say, let's do 6 over 3 plus x. We'll keep it centered at 0 for now, while we're still looking at these first couple of problems. There we go. Same situation. We want to make sure we have x minus c here, but since the center is 0, that just has to be an x, which is good. Next thing, we want to make this into a 1. In order to make that 3 into a 1, the only way we can do that is to divide by that number. Okay? So we'll divide all of our, we can't just divide this number by 3, of course. We need to divide every number by 3. So we'll do 1/3 over 1/3 times 6 over 3 plus x. So that'll make it a 2 on top, 1 plus x over 3 on bottom. Now, the 2 is of course extra on the numerator, so let's factor that out. So it's 1 over 1 plus x over 3. And this is kind of the usual course that we would take, or the usual approach that we take. So try to get a 1 here and here, and then whatever is here, we know this will be what's raised to a power inside the power series. Okay? And this is just an extra multiplier on the outside of the power series. So for our power series, we know it'll be a 2 in a summation, n equals 0 to infinity. And the question is, what happens in this situation? 1 over 1 plus x over 3. Well, we know from here, this is our formulas again, 1 over 1 minus f of x is f of x to the n. So we've got x over 3 to the n, but the fact that it's a plus, that's where we bring this element in. If it's a plus x, or plus x minus c, we know it's going to be an alternating term also. So what we really have is a combination of these two rules, where we have a function raised to the nth power, and we also have an alternating term, -1 to the nth power. So it looks something like that. And that would be our power series here. Now, as far as, and I drew a line, but we still need to talk about the radius of convergence. For convergence, Again, whatever is inside here, this is x over 3, has to be between negative 1 and 1. Okay. And so we'll just multiply everything by 3 there. So negative 3 less than x less than 3. Okay. It's actually not too difficult to find the radius of convergence. I may not even ask you that part on the test because we've already done it so much up to this point. The book, however, if you look at the problems, it does ask you this, so I wanted to make sure at least you would know how to do that. But I'm not going to specifically ask for it in this problem, I'm just looking for the power series. And you'll see, you probably saw that in how I created these questions for the practice test. It'll be the same on the actual test. Okay. This is a little bit longer test as a result. I think it came out to be, what, 14, 15 questions? Seems a little bit longer than our normal tests have been, our previous couple of tests have been at least. Anyway, let's continue. What should we center this at? Let's center this at x equal, or at, what's it? C equals 2. I have a hard time remembering that for some reason. Okay. So the other ones we've done are centered at 0 so far. This one we want centered at c equals 2. Now, what that means, if it's centered at c equals 2, then we want this to be x minus 2. Okay, so whatever the center is, we want x minus the center to be right here. Okay, and so the question is, we already have this number here. How does that number change to account for this change? And that's what I did in the first example. Probably it was a little too early to dive into that, so I apologize for mixing up the order I wanted to do these in. Does anyone have an idea what this number should be, just looking at this? It's a question of balancing. Like from here to here, we had to subtract 2 from x. So to balance out the subtraction of 2, we have to add 2. So we can make this a 6. And so we think about that. If we combine these back together, do we get back to 4 plus x? Well, if we take 6 plus negative 2, that makes 4, and we have plus x. So this does simplify back to the same thing. What we're really doing is rewriting it in a certain form that allows us to represent the center being 2. It's not that we're changing the equation, we're just writing it in a way that's more convenient for us in this particular instance. But it does have an overall impact of what we're doing. Okay, so if we subtract 2 here, then effectively we need to add 2 here to balance that out. Now again, this subtraction by 2, we have to make sure it agrees with this sign. Now, this is a plus sign, so we're actually okay here. So this will be minus 2, that makes it a plus 2, so it turns into a 6. Our next step is to get a 1 here, and then to get a 1 up here, like we had previously. To get a 1 in this first position on the bottom, we divide everything by this number, so we'll have to divide everything by 6. Both on top and on bottom. Okay. Now on top, 1/6 times 2, or 2 over 6, we know that's 1/3 in the numerator. Now the denominator, 1/6 times 6 is 1. And then we'll have plus x minus 2 over 6. Finally, we just want a 1 in the numerator, so we'll factor out our 1/3. There we go. Now we're ready to create a power series for this term. Now, this is actually a lot like what we saw in the example above, except it's now centered at 2 instead of 0. Again, we have a plus down here, and the fact that we have a plus means it's going to have an alternating term. The other thing is that whatever function is here, we know that's going to be raised to the nth power. So we'll just put those two together, basically, once again. So that'll be 1/3 times the summation equals 0 to infinity. We'll do -1 to the n times x minus 2 over 6 to the n. And that is our power series. Okay. It's really a matter of adjusting to the patterns here, and I'll give you the foundational formulas here that everything else is based on. This is what I'll present in your formula sheet. I didn't quite give you that much on the practice test. I'll make sure I update it on the actual test to include these other ones. I think that'll be helpful. So we're just trying to match things up with one of these patterns, or a combination of these patterns in some cases. Understandably, the convergence interval here will be between -1 less than x minus 2 over 6 less than 1. So we multiply everything by 6. And then we'll add 2 everywhere. So what would that be? -4 less than x less than 8 is our radius of convergence, or a domain, whatever you want to call it. Okay. Let me do another example. This one we'll say is centered at -2. Now, how are we going to do this? First thing we do is we want to make sure we account for the center in the way that this is written. So be x minus the center will be x plus 2. So x minus the -2 changes to a positive. Okay. Now, we say x plus 2, but really there's a negative on the outside of that, so technically this is a -2 that we've just introduced into our denominator. So by introducing a -2, we also have to introduce a +2, so we'll make that a 5. Okay. Again, it's just a balancing act. This is technically a -2, so we add put a +2 with the other term, and that makes it a 5 from the original 3. Notice if we simplify, 5 minus 2 is 3 minus x. Gets us back to the original form. Okay. Next thing is divide everything by 5, because we got the center where we need it to be, and now we just need a 1 minus that value next. So that'll be 1/5 over 1/5 times 1 over 5 minus x plus 2. So it makes it a 1/5 on top, and then a 1 minus x plus 2 over 5 on bottom. And again, this 1/5 on top we can factor out. This is 1 over 1 minus x plus 2 over 5. Now we can make that into a power series. And again, that follows our 1 over 1 minus f of x pattern, which is f of x to the n. So it's x plus 2 over 5 to the nth power. And that would be our summation. Okay. Now, in some cases, we can go a little bit further if we need to. Let's see. I want to look at number... Well, let's do 18. This is on page 666. Let's hope that's not portentous. So we have 5 over 4 minus x squared. C equals 0. There's really two ways we could do this. I wanted to do this before 16 because I didn't want to kind of confuse the issue. Well, not 16. There's another one I want to do later, but I might do 16 next. Yeah. Anyway, it's centered at 0 just to make it a little bit easier on us, because these are hard enough already without changing center or anything like that. But notice that even though it's x squared instead of x, we're actually okay. You know, it's still, you know, if we can get it to this format here, 1 over 1 minus f of x, even if that includes an x squared, that's all right. Okay, it doesn't have to be just x; it could be x squared. There are some other things we need to consider, but so we certainly have the 5 and the 4 to deal with. Excuse me. But we'll deal with that in a moment. Well, I mean, we can go ahead and get rid of the 4 by dividing everything by 4. Okay. Factoring out the 5/4. Again, same steps that we would normally do. And then this is 1 over 1 minus f of x. We know it's this thing to the nth power inside. So we get 5/4 times the sum, n equals 0 to infinity of x squared over 4 to the nth power. And that's actually good enough. Now we could say x to the 2n over 4 to the n if we prefer, but we can leave it like that. Okay. Sorry. So even though that was x squared instead of x, we're still able to proceed as normal. If we had not been centered at 0, that would have been a different story, but we're not going to worry about that one, because it gets a little crazy. So. But I want to look at 16. This is very clearly not the same question that we've been looking at so far. We have g of x is equal to 3x minus 8 over 3x squared plus 5x minus 2. Now, we look at this and say, well, this is nothing like what we've looked at so far. And again, what we know is, again, our formulas. And our formulas only work if we have, one of these situations or very similar. This is centered at 0 also. So we don't have to worry about that. But, we have these formulas, and that's all we have, And essentially what we need on the denominator is a binomial of some kind. And that's really the indicator as far as what needs to happen in this problem. Right now, we have this trinomial. We know it's factorable. We could say, let's say it's 3x minus 8 on top. Let's see, it's 3x, x, this will be a 2, this will be a 1, that's a plus, that's a minus. So we can factor the denominator, so it's 3x minus 8 over 3x minus 1 times x plus 2. Wouldn't it be great, though, if we could just have one denominator be 3x minus 1 and the other denominator be x plus 2? If we had them like this, we could actually work with our power series formulas that we have. Well, it turns out that we do have a mechanism for doing that, and we studied it in the previous chapter, and that is a partial fractions method that we can use here. The method of partial fractions says that we have unique factors here, so we can make this one unknown constant over one part of that denominator plus another unknown constant over the other part. Alright, so yeah, let's let's continue. Excuse me. So we have to do our partial fractions first, and so remember what we do here. We multiply on top, bottom, but well, multiply every numerator by the original denominator. Sorry, 3x minus 1 times x plus 2. And so let's see, that would just give us 3x minus 8. A times x plus 2, and b times 3x minus 1. We distribute. Okay. And then our x's, we know those will all be equal to each other, and then our constants, so those will be equal to each other. So for our x's, we have 3x equals ax plus 3bx, so we can say 3 is equal to a plus 3b. And for our constants, we have negative 8 is equal to 2a minus b. 2a minus b. Alright, and so this is the system of equations that, this is the system of equations that we would like to solve. Now, there's two ways we can go about doing this. Use either a substitution or elimination. Personally, I prefer elimination. Because we can just multiply this equation by 3, for instance. First equation is the same still. Second equation we multiply by 3. And now we add them together, and the b's cancel out by design. So again, negative 21 equals 7a, which is great. Because a will be a whole number. A is negative 3. Because of that, okay, sorry about that. And now, knowing that a is negative 3, we can plug it back into one of these two equations to solve for b. Personally, I think the first one will be a little bit easier. Okay. So that will give us, add that over, so it's 6 equals 3b. So b is equal to 2. So we calculated a and b. And now we can rewrite g of x. Now remember up here, we said a over 3x minus 1 plus b over x plus 2. And we'll just fill in the values for a and b that we found there. Okay, so a was negative 3 over 3x minus 1. And b is 2 over x plus 2. Now, we successfully completed partial fractions. Now we can find a power series for each of these terms individually, where we could not find a power series for the original term. And that's the whole point, is even though we couldn't find a power series for the original expression, we are able to find a power series for these two expressions separately. And g of x will be just represented by a sum of power series as a result. Let's go to the next page, though. Alright. So let me rewrite g of x first. And Thank goodness this is still centered at 0, because this would be a nightmare otherwise. Even more so, I guess, than it already is. Okay, there we go. Whoops. Here you go. That's what we have. Now, one thing that we'll notice, and again, if we look at our formulas, we always have x second in our formulas, so let's go ahead and switch up that order first, just to get it back to what we're used to seeing. So it would be negative 3 over 1 plus 3x plus 2 over 2 plus x. Not a huge change, since both denominators are... wait a minute. I thought one of them had a negative in it. Sure did do that. Okay. Sorry, that should be a minus. So this is a minus 1 plus 3x. Yeah, sorry I messed that up when I translated over to the other side of the page. This is 3x minus 1, so when you switch them, it's actually negative 1 plus 3x, which it's not a huge deal. It'll actually be pretty easy to take care of. So in this first expression, we don't worry about the fact that x is multiplied by 3. That doesn't really affect anything as far as the center being 0. 3 times 0 is still 0. So we just continue trying to get this to be 1 and then this to be 1. And the same here. This to be 1, this to be 1. Now if we want this to be a positive 1, we'll multiply everything by negative 1, top and bottom. And here we have to divide by 2 everywhere. That'll get us, let's see, that'll be a 3 over 1 minus 3x. And this will be a 1, it's convenient, over a 1 plus x over 2. Okay. Getting closer. We do need to get rid of this 3 in the numerator, but again, we can just factor that out. So 3 times, and I'll move this up a little bit, 1 over 1 minus 3x plus 1 over 1 plus x over 2. Now again, these have the 1s where we need them to be, and then these expressions are what's raised to a power. And if it's plus, we know there's also an alternating term involved. So to create the power series from here, this is 3 times the sum, n equals 0 to infinity, of 3x to the nth power, plus the sum from n equals 0 to infinity. This is plus, so we'll have an alternating term, and x over 2 to the n. And so that is our power series expression for the original function here, which is g of x equals 3x minus 8 over 3x squared plus 5x minus 2. More than likely, we're not going to be able to combine these power series together. However, one thing that it does affect is the radius of convergence. So what's going to happen is each of these has a different radius of convergence. And what we would actually like to find for the overall radius of convergence is the intersection of these two individual radii of convergence. So this one says negative 1 has to be less than 3x, which is less than 1. This one says that negative 1 has to be less than x over 2 is less than negative 1/3 less than x less than 1/3. This would be negative 2 less than x less than 2. Basically, we want the more restrictive value on each side. Now, if we picture it on a number line, we want where the two things overlap. So where do these overlap on a number line? Well, this one's entirely contained inside this one, so this is where they overlap. This is the radius of convergence, or interval of convergence. Okay. Alright, let me show you another problem. This is 26. That one took a whole page. Jeez. Now, you're probably getting worried at this point. I'm going to give you one of these on the test. Well, you can already see from the practice test. If I didn't give you one of these on the practice test, I'm not going to give you one on the real test. So, don't panic. That's my message to you there. I'm not going to do that to you. I think it's an interesting problem, but a little bit too close to the end of the semester to be worried about that. Let's look at 26. And the question here is, how would we create a power series for f of x equals natural log of x squared plus 1? Focus. Almost like a Jedi mind trick there. Alright. And this is an entirely different issue than we faced in the last example, because at least in the last example we could use partial fractions. Now, this one's nothing like, again, the formulas that we were looking at. Okay? But we have another tool at our disposal. This tool is the derivative function. Even though we cannot find a power series for natural log of x squared plus 1, I think we can find a power series for f prime of x. Let's look at the derivative first. Now, for a logarithm derivative, whatever is inside goes on the denominator, and then we take its derivative and put it on the numerator. So it's 2x over x squared plus 1. So we need to make a power series for 2x over x squared plus 1. And then that'll be for f prime, and then we'll worry about it from there. There's going to be another step, though. Notice on the bottom, we'll certainly want to rewrite that as 1 plus x squared, and that's just a matter of putting in the right order. Again, these are centered at 0, which is a mercy. Okay. So we have our correct center here. That's no big deal. And we already have a 1 here. That's great. We just need a 1 up here. So we can just factor out our 2x times 1 over 1 plus x squared. We can create our power series here and then proceed from that point. So f prime of x is going to be 2x times the sum, n equals 0 to infinity. Now, this is a plus, so we know that means it's an alternating term, negative 1 to the n. And then we have x squared is our function, that's raised to the nth power. Now, this one, it turns out we can simplify a bit, and actually, there's going to be another step here, but before we get to that, I absolutely recommend that we simplify this. X squared to the n is kind of messy because we have something raised to a power raised to another power. But again, we know we can simplify this to x to the 2n. Okay, because we know if we have x to a power raised to another power, we multiply those two powers together. 2 times n is 2n. The other issue that's here is we have x currently appearing in two different places. So what we can do is we can take this x and bring it inside and join it with the other x's. And remember, this is x to the first on the outside. Since it doesn't have any ends, it can cross this boundary inside. This one cannot cross the boundary going out because it does have ends. And this whole summation is n going from 0 to infinity, so this one cannot be moved outside the sum, but we can move this one inside the sum with the others. It's an important distinction. It's also important that we know that we're still working with f prime. And I'll get to that in a second. Now, this is x to the first, this is x to the 2n. If we're multiplying these together, which technically they are multiplied, then we add their exponents. So 1 plus 2n will make 2n plus 1. So in this situation, that's definitely how we would like to proceed to create our power series. We want to make sure that x is just raised to a single expression. It's not like x squared to the n times another x on the outside. That's a little bit complicated. We prefer to simplify it to this extent. Because we have one more step, and that is we're trying to find a power series for f of x. What we've found is a power series for f prime of x. So how do we go from f prime of x to f of x? Well, to go from f prime to f, we're going to have to integrate. Okay, and this goes back to what we discussed at the end of last class in how we would integrate a power series. So we know integral of f prime is just f. We know the 2 is not going to change. Our summation doesn't change on the integral. It does change on the derivative. But what we do is we're only integrating the part with x. We're integrating with respect to x specifically. So this is the only part that ends up being integrated, this term. So make it x, and this is just a power rule. We add 1 to the exponent and then divide by the exponent. This is 2n plus 2, and then we divide 2n plus 2. So that's our power series for f of x. And we can just say that's our power series for natural log of x squared plus 1. Oh, I am leaving out something very important, and some of you are probably thinking that and say, hey, where's the plus c from the integration? And that's a good point. There is a plus c here. However, it also turns out that c will be 0 in this point, but let's figure out why that is. And that's why I did that, because I knew it was going to be 0, but I need to still show you why it's 0. If we go back to the original function, our original function is natural log of x squared plus 1. Well, what is f of 0 then? Well, f of 0 is natural log of 0 squared plus 1, which is natural log of 1, which is 0. So essentially, we have the condition that f of 0 should equal to 0. That should allow us to solve for c. And theoretically, I could pick any number there. I pick 0 because it works out relatively nicely, and 0 specifically is very easy to work with power series. You'll see why in a second. So we go back here, and we know f of 0 is equal to 0 from the original function. Well, if we plug in f of 0, we get 2 sum n equal 0 to infinity, negative 1 to the n, 0 to the 2n plus 2 power, 2n plus 2 plus c is equal to 0. Well, ultimately, this 0 being here zeroes out the entire summation. Because whatever happens with this term, whatever happens with this term, what happens with these? 0 raised to a power is 0, 0 times anything else is 0, and 0 divided by anything else is 0. That x being 0 just zeroes out the entire summation. So we're just adding up a bunch of zeros, which is 0. It doesn't matter if we multiply by 2 either, because it's still 2 times 0. So long story short, this is equal to 0, so our conclusion is c must be equal to 0 also. So we don't really need that term in this case. I mean, we need it, but it turned out to be 0. So that's one thing that we'll have to make sure that we do whenever we do this this process, which is we differentiated the expression, we found a power series, and then we integrated again to get a power series for the original function. Okay, and it could be that in other cases we have to integrate something, get a power series, and then differentiate. There's different ways that we might have to proceed. It really just depends on the function that we're working with. One more type of problem I would like us to look at. And let me take advantage of that problem that we just worked. Let's say we want to approximate the integral from 0 to 0.3 of natural log of x squared plus 1 dx using power series. Okay. Well, we already found a power series for a natural log of x squared plus 1, and that's the good news. Natural log of x squared plus 1, we discovered, is equal to 2 times the sum n equals 0 to infinity, negative 1 to the n, x to the 2n plus 2 over 2n plus 2. Okay, so that means we want the integral from 0 to 0.3 of the power series n equals 0 to infinity, negative 1 to the n, x to the 2n plus 2 over 2n plus 2 dx. So we want to integrate the power series. Now this is a definite integral, so we don't need the constant of integration, which is good because we no longer have a means of attaining it. We had a means before working with the natural log function because we had the original natural log function as f of x. This time we don't know what the integral of this is going to be. It's whatever the integral of natural log of x squared plus 1 would be. And the idea is that this, we may or may not be able to integrate this ourselves using, we would have to use integration by parts to figure that out. I'll look at that after we do this to see if we can get a comparison. The reason we would even use this approach to begin with is that it may be that this cannot be integrated, and this is the only way we can approximate this value is by letting this function be represented by its power series, integrating the power series, and then plugging in the limits for x. Okay? And this is, you'll notice, is the last problem on the review is one like this. But, as I've done here, I've given you the power series for the function. So, that part is taken care of, at least. Let's see. So we want to integrate the power series. Now again, when we integrate the power series, the only part we're integrating is the part that has x itself, which is x raised to a power. Because notice our differential is with respect to x. And so we're just focusing on the x variable. Everything else stays the same. Now, x, we use the power rule to integrate, so we'll add 1 to the exponent. This will be 2n plus 3. And we divide by that exponent, 2n plus 3. Okay. So this is the expression that we have. This is our power series, and we want to evaluate it between these values. Now, we know what happened the last time we plugged in 0 to a power series. X is 0 here, it just zeroes out the whole thing. So plugging in the bottom limit of 0 just makes a big 0. So really we only need to plug in 0.3. So we'll make that the 2 sum n equals 0 to infinity, negative 1 to the n, 0.3 to the 2n plus 3 over 2n plus 2 times 2n plus 3. Here's the issue, though. With this value of 0.3 plugged in for x, this is still an infinite series. It's no longer a power series, it's just an infinite series, but it's still infinite. Infinite being the key word. So, the issue is we don't actually know what this is going to equal exactly. We can't know what it will equal exactly. All we can do is estimate it. So, luckily, the best way to estimate this is just by plugging in the first few values of n, and that'll give us a nice estimate for the result. So let's say we want to approximate using the first 4 terms of the series. Okay. Now I'll keep the 2 outside for now, but we'll have to plug in n equals 0, n equals 1, n equals 2, and n equals 3. And then we'll get our result based on that. Okay? This is where we'll definitely want a calculator. Alright. So we start n equals 0. That's the first term of our series. Negative 1 to the 0 is positive 1. So we know this one's positive. 2 times 0 plus 3 is 3. So I have 0.3 to the third. I'll put that into calculator. 0.3 raised to the third power. Okay. And then divided by 2 times 0 plus 2, 2 times 2 times 0 plus 3, 3. 2 times 3 would be 6, so I divide that by 6. So we get 0.0045. Okay, and now we just repeat this for the rest of it from there. The next term is that n equals 1. Negative 1 to the 1 is negative 1, so we know it's going to be a negative. 0.3 is raised to the 2 times 1 plus 3. So that'll be 0.3 raised to the fifth. 2 times 1 is 2, plus 3 is 5. Yeah. Okay. On bottom, 2 times 1 plus 2, that'll be 4. 2 times 1 plus 3 will be 5. 4 times 5 is 20. So I'll divide this by 20. And we get 0.0001215. Whoops, sorry. 0.0001215. We're already pretty accurate, I would say. 3 decimal. Now, essentially, our level of accuracy, however many leading zeros we have, like we have 3 leading zeros, that means we basically have three decimal places of accuracy at the moment, just at this second value of this expansion. So we're gonna get some really small numbers here, it sounds like, but it'll be okay. It's definitely gonna be more zeros next time. Even this first number was already accurate to 2 decimal places. Okay. So n equals 2. Negative 1 squared will be a positive, so we know this will be a plus. 2 times 2 plus 3, that'll be 4 plus 3 is 7. So 0.3 raised to the 7th power will be our numerator. Okay. 2 times 2 is 4, plus 2 is 6. 2 times 2 is 4, plus 3 is 7. 6 times 7 is 42, so I'll divide that by 42. So we get 5 leading zeros and then 5, 2. Okay. 5207. And the next one will definitely be negative because we know a plus minus plus minus. Sorry for not leaving enough room here. N equals 3, that would be negative. 1 cubed is negative. 2 times 3 plus 3 is 9, so we'll take 0.3 to the 9th. Two times 3 plus 2 is 6. 8. 8, sorry. 2 times 3 plus 3 is 9, so 8 times 9 is 72. I'll divide by 72. So we get 6 leading zeros and then 273. 1, 2, 3, 4, 5, 6. 273. Alright, and now I'll just put these 4 numbers all together and then multiply by 2, and we have our approximation. So we take 0.0045 minus 0.0001215 plus 0.00005207 minus 0.000000273. So I got that result, and then I multiply by 2, and we get the answer 0.008766868. I'll just write that down here. Okay. Now, let's see if we can figure this out exactly. Like, is it possible that we could actually integrate the original expression, natural log of x squared plus 1? I'm not going to make you do this part of the test. This is just for my own curiosity at this point. And I want to see if we can actually, if we can integrate that, then we'll be able to figure out the actual value, and it'll be nice to compare it to our estimated value. I'm hoping we can integrate it. That'd be cool if we can compare. Alright. Now, the issue is with logarithm, anytime we have a natural log inside of our integration, we know it's a partial fraction, not partial fraction, it's integration by parts, and we have to let u equal the logarithm. So we'll let u equals natural log of x squared plus 1. That just leaves dv to be the dx in the expression. Now our derivative of this, we already said, was 2x over x squared plus 1. And the integral of dx is just x. Okay. We're still in the realm of possibility as far as integrals go. Our pattern, remember, is uv minus integral v du. uv is x times natural log of x squared plus 1 minus, and then v times du. Now, would multiply this x by the numerator. There's a dx there. And so that would be 2x squared over x squared plus 1. dx. Now, anytime our exponent on top is equal to or greater than the exponent on the bottom, such as we have here, we can actually divide these two. I don't know if what's going to be left is going to be solvable, but we'll see what we can do. So we need to take 2x squared and divide that by x squared plus 1. That's long division. My goodness. These 2x squared plus 2, those are subtracted. So we had a remainder of minus 2. So the result of the division is 2 minus 2 over x squared plus 1. This is going to be not the most enjoyable integral ever, but it's doable. Definitely we can actually integrate this, which is nice. Now this is the first part. Now again, this is subtracted, so we have to be careful. And I just blew this placement here, so I apologize. I'm just going to rewrite this line a little bit lower where I should have written it. So minus integral of 2 minus 2 over x squared plus 1 dx. I wonder if it's beneficial just to factor out the 2. Since both parts have that 2 there, that might make it a little bit nicer. Okay, so this will be x natural log of x squared plus 1 minus 2 times, this will be x minus arctangent x. And that's evaluated from 0 to 0.3. Let's see. Now, I think 0 is going to zero out everything here. Arctangent of 0 is 0, 0. Natural log of 1 is 0, 0. Yeah. 0 is going to nix everything here, so we just need to plug in the 0.3. Let's see. So we need 0.3 squared plus 1. Take the natural log of that value. Not reset the memory. Not clear the memory. Sorry. The natural log of our stored value. It's no longer stored. I'm going to start over. I'm sorry, guys. 0.3 squared plus 1. Take the natural log of 1.09. Much easier that way. Okay. Times 0.3 in front. Got that. Okay. Then minus 2. I'll put parentheses. 2 times, and then put another parentheses for what's in here. So it'll be 0.3 minus arctan of 0.3. Arctangent will be second tangent. 0.3. Close both parentheses, and there's our result. 0.0087668897. And we compare that now with the value that we got from the first 4 terms of our power series approximation. 0.00876688, and then right here we see the difference. So it's actually really close. There are 1, 2, 3, 4, 5, 6, 7 decimal places of accuracy with only the first 4 terms of that approximation, which is really nice that it only takes 4 terms to be this accurate. It depends on going from one function to another, but it turns out for logarithm it actually goes kind of nice. Now, what I will do on the test, and you'll see this on the practice test also, is that instead of having you like do it by hand, I actually just gave you the actual value. Let me bring it up on the screen. Let's see. First thing, I gotta switch to the screen. Sorry about that. So let's see. Go to calculus. Which is here. Files. Test 3 practice test, which I uploaded last Thursday, as promised. Took a little bit longer, so I had to rewrite some sections, but I got it done. You'll notice this is a little bit wonky, like with the spacing here. I wouldn't normally leave it like that, but honestly, I don't have the same software here at home that I do at work, which is unfortunate. Anyway, so you can kind of... That should be good. So you can see, find the next 2 terms of the sequence. That should be pretty straightforward. Just basically looking at the pattern on the numerator and the denominator. Determine the power series, would determine whether the series is convergent or divergent. If it's convergent, find its sum. This is actually a geometric series, and it'll be the same on the actual test. So you have to find, you have the first term, you have to figure out what the ratio R is, then use the, first of all, knowing what R is. This is on the formula sheet. For a geometric series, it converges when absolute value of R is less than 1. And in that case, the sum is S equals A over 1 minus R. And it diverges when the absolute value of R is greater than 1. I think it's greater than or equal to, but I'll leave it at that. So I gave you a sheet with all these different tests on them. The format, how the test works, the condition for convergence, and the condition for divergence. Notice that nth term cannot be used to show convergence. Okay, so we have that. Now, geometric means that, if the ratio is less than 1, then we know it converges, then we can use this formula to find the sum. If the ratio is greater than 1, then we won't do that. So this is back where we are. The third problem, use the integral test to determine convergence or divergence. So just use the integral test there. 4 through 11 don't really tell us what tests, so it's really a matter of figuring out, what are we looking at here. And when we go over this review or this practice test on Thursday this week, I'll go over each of these problems. So we'll talk about that as we go. Like especially these problems 4 through 11, kind of what we're looking for as far as how do we know it's one thing versus another thing, and hopefully that'll inform you going into this exam what we need to do. Again, every problem is just be a file upload question, and you have to upload your answer. I'll probably give you a little bit more time in this test because I'm worried that you might not be able to do it in 2 hours, so I'll probably give you a 3-hour time limit just in case. And again, if you do have any trouble uploading files, then just email me them instead. Yeah. So those. 8 through 11, these 4, so 8 of those total that we do it like that. 12, here's our function, find a Taylor polynomial centered at x equals 2 and using n equals 4. And then test the accuracy of the polynomial by finding P4 of 2.5 and comparing it to the actual value of e to the first. I'm not positive this part's correct, whether it should actually equal that or not, but we'll discover that together on Thursday. Radius of convergence for a power series, we talked about that last time. So this was last Tuesday, this was last Thursday, this one also. And then this stuff is for today, these 3 problems, 15, 16, and 17. These, we're given the function, and you want to find a power series for the given function centered at the indicated value. So 3 over 1 minus 2x centered at 0. We just go through our same process there. Likewise here with the center of -1. So. But then this is the one I wanted to look at with integral 0 to 0.7 x squared over 1 plus x to the 6th. It gave you the power series. This should be x to the 6th here, I'm sorry. I gave you the power series. Oh no, I didn't. This should be 6n plus 2. Make sure when you practice this, I'm sorry about this. This actually is a true statement because I made 2 consecutive mistakes. Here, I meant to write down the same expression. So this would be 1 plus x to the 6th. This would be 6n plus 2 as a result. So when we practice this, make sure you address that change. But what I wanted to point out is I went ahead and just gave you the approximate value. So the answer that we get using the first 4 terms for this integral, so we just like we did in this last example, we take our power series, replace it here, integrate the power series, and then plug in the limits, and then evaluate the first 4 terms, pretty much like we just did. But instead of going through and integrating this by hand, I've already done that for you and given you the approximate value. That way we can know how, if we've done it correctly, we should be pretty close to the approximate value. It won't necessarily be exactly the same, but it should be real close. And then, of course, the formulas, convergence formulas, all of those, but then also Taylor polynomials, radius of convergence for power series. And I probably should expand that a little bit. And then the geometric power series formulas, I'll expand those too. So I'll fix that on the test, what I've not gotten correct here. So I apologize for that. Anyway. Do you have any questions? So next time we will work on the practice test. Keep in mind what I pointed out about problem 17 being incorrect. Need some extra sixes in there. But we'll go over each of those problems. If it takes a little bit longer, if we go into beyond class time, I'll make sure I keep going and finish it. Even if you need to go to another class, it's fine. You can come back and watch it later if you need to. I don't know if it'll take me more than 2 hours to go over that practice test, but it might. 17 problems, it'll take a bit of time. And that's especially why I think I will give you a little bit more time than usual on the actual exam, so that you'll have enough time to get through everything. So I may even go up to like 4 hours. I don't know. If any of you are concerned, let me know. I don't want it to be that long of a test, but it might be. Okay, we will stop there today. That's the end of class anyway. It's not that often this semester we made it to the end of class and then had to stop, but here we are. You all have a good rest of the day, and we will continue on Thursday. Y'all take care. Bye.